Alrighty, so this is going to be the second example of Dijkstra algorithm we're going to do, and here we have the setup. Right, we want the shortest path from A to G, and this is the graph we're going to be working on. So, like before, right, we want to go from A to G, so we're going to mark the vertex we want to finish off on, which is going to be G. Okay, and then we're going to ask ourselves, right, we're looking at a vertex, and we got to give it a number, right, now that we're talking about it. Since G is the last vertex, right, this number, normally for all these examples, is going to be the distance from a vertex to G. And in this case, right, G is, well, just G. So we're going to put A0 right here. Okay, and so now, right, just like the first example, we're going to start talking about the edges, right, that are connecting to G right here. So we got two of them, U and U. And now we're going to look at the vertices that those things are attached to. All right, then we're going to pick the one that is, that's going to have a smaller number. And so in this case, it's going to be E. Right? Why is that? Well, E doesn't have a number right now. And we haven't given it a little number in a box. So when we give it the number, right, for any time we're visiting a vertex that doesn't have a number yet, we're going to give it the number of the vertex it connects to plus the weight of this edge. Is 2 and 0. So in here is going to be 2 plus 0, which is 2. Right, and then for F, same thing. It doesn't have a number, so I'm going to give it 1, and it's going to be the weight of the edge that we're looking at, plus the number attached to the vertex that it's connected to. That's going to be 5 plus 0. Well, 5 plus 0 is the same as just 5. Okay, so these two edges we've already talked about, so we're going to mark them down. And then, check it out, right? We've talked about all the edges attached to G, so we're going to call G visited, and we're done with it for now. So then, now we got to talk about one of these green guys, right? The vertices that we were just talking about, E and F, and the one we're going to talk about first, always, is going to be the one with the smallest value, right? The smallest number in here. So what do we got? F has 5, E has 2. So the one we're going to talk about is going to be E. We're going to talk about this guy first. Okay, we're going to mark down the edges that are attached to E that we haven't talked about yet. So E has 4 edges that are connected to it, which is this guy, this one, and this one. But we've already talked about this one over here, right? The edge EG. So we're just going to now talk about these 3. Okay. And then the order of what we're doing here doesn't really matter all too much. All we're going to do is look at these vertices and then ask, right, does it have a number? And if it doesn't, right, we're going to give it a number just like we did for E and F. And if it does have a number, we're going to ask if the number that the vertex already has, if that's going to be less than or equal to us taking a little detour. And again, I'll explain what a little detour means in this case. So let's do the easy ones first. Right? D doesn't have a number, so what we're going to do is that we're going to give D the number, right, the value of the edge, plus the value of the vertex that's connected to it. So that's 7 plus 2, so D is going to get 9. We're going to mark this edge, we already talked about it. C doesn't have a number either, so we're going to give it the same treatment. Right? The number we're going to give it is going to be the value of the edge plus the value of the number attached to that edge. Right, the edge you're talking about is the one connecting C and E, so there's going to be the weight of CE plus whatever E has. So 3 plus 2, 5. So we're going to mark this, and now we're going to talk about this last edge connecting E and F. And so F, right, unlike D and C, already has a number. So what we're going to be asking ourselves is this. Is it faster for F to go to G, either with the path we already have, which is this guy, or if from F we do a little detour to E? And so I'm going to draw those paths out. But the question is this faster? Is there OG path? Or is this faster? Right, us taking a detour. Okay. And then if you want to check that, right, we're going to be doing what we did before, which is just adding the length of these edges. So this is just 5. So maybe I'll write it in a yellow. Right, the length of this is 5. And the length of this guy is 1 plus 2 or 3. So clearly, right, 3 is smaller. And so since 3 is smaller, what we're going to do is that we're going to update what we have for F. Right. What we found was that, F's original path that we had, what's this, is slower than us taking a detour through E and taking this path. And remember, whenever we're visiting a vertice, we care about the distance of that vertice to our end. So in this case, we want to see what's the fastest way for, if we started at F to get to G. Right? Originally, again, we had this, which is length 5, but now we realize that doing this is faster. And so, like I said, right, we're going to give this guy a number. Right, and then we're going to give it was the length of that edge, or the length of that path that we found, which we said was 3. Okay. And then I'm going to mark new vertices that we talked about in this step, which is D and C. And then we've already talked about all the edges attached to E, right? I've colored all these in a nice solid blue. So I'm going to mark this, and we're going to call E visited. Okay, and then from here, right, we have 3 vertices we can talk about. We can talk about D, we can talk about C, or F. And how are we going to pick this? We're going to pick the vertices we're going to talk about based on which one of these has the smallest number. So F has 3, C has 5, D has 9. And so clearly, right, 3 is the smallest, so we're going to talk about F next. All right. And so since we're talking about F, we're going to talk about all the edges that it's attached to. So we can't talk about this one anymore because we already marked it. Can't talk about this one because we already marked it. So the one that's left is this guy. Okay. And what is it connecting to? Connecting to vertex B. So we're going to start talking about B. So does B have a number? And the answer is no, right? I haven't given it a little number yet. So since it doesn't have one yet, the number I'm going to give it is going to be the weight, right, the length, whichever word you want to use, of the edge that we're talking about, which is 2, plus the number that is attached to F. So 2 plus 3 is 5. We're done talking about this fella, so we're going to mark this edge. By doing that, right, we see that we've marked all the edges that F's attached to, so we're going to call F visited. Right, I'm going to label B with this green here because we've now just talked about it. And then from here, right, we got to pick, what should be the next vertex you're talking about. And the choices that we have are going to be these green guys. So D, C, and B. And how are we going to pick? Again, we're going to pick the one that has the smallest number. So in this case, where we have a tie, B has 5, C has 5. So we can choose, right? Either way is going to get us to the right answer. So since I want to do this top to bottom, I'm just going to pick B first. Right, but you could go C first. So we're going to talk about all the edges attached to B. We've already talked about this one on the right, so we're going to now talk about this one that's connected to A. Okay. Does A have a number? I think the answer is going to be no. So what we're going to do is we're going to give it 1, and just like before, the number we're going to give it is going to be the weight of the edge plus the value of the vertices that we're talking about. So 12 plus 5, 17. We finished talking about this. We're going to mark it. We notice that, hey, we've talked about all the edges attached to B. We're going to call B visited. Okay. And now you're going to notice that I'm not going to mark A as green. And I mean, that's just because right, it's the starting indice, or the starting vertice. But I mean, even if we're using the same rule that we were using before, where we talk about the one with the smallest value out of all of them, I mean, A is still way bigger than the values of C and D. Okay, so out of these two, we're going to talk about C. Why? Because C has 5, D has 9, 5 is smaller. We're talking about all the edges it's attached to, which we already talked about the one connecting to E. We're going to talk about the one connecting to D and the one connecting to A. Okay, so D right now has a 9, and we're going to be right now focusing on D, and we're going to ask ourselves this. Right now, the path from D to G is this. Right, that's how we got this 9. And so what we're going to ask ourselves is it faster for us to start at D, take a detour to C, and then follow the path that C had, which looks like this. And so to check, right, we're going to be doing, we're just going to draw these paths out. Now, you don't have to do this. Really what we're doing is we're comparing 9 versus the length of this edge plus the value of C. But I'm illustrating it just to prove, the intuition of what we're doing. So T, C, E, G. This is versus D, E, G. All right, this 2, 3, and 2. Right. If we add all these up, right, we're going to get this one on the right-hand side is 7 plus 2. That's 9. And the one on the left is 2 plus 3 plus 2, which is 7. So 7 is smaller than 9. And because we found a number that's smaller, right, or in this case, we found a path that's faster for D, we're going to update D to have that number. So right now it has 9. And so we're going to update it to have 7. Okay, and then we're going to mark this edge. And now we're going to look at A, right? This edge right here. A already has a number, so we're going to do the same exact thing we did before. Right? We want to see, is going through C faster or is it slower? And I'm realizing now, about 10, 12 minutes into this recording, that I haven't given a weight to this yet. So I'm going to give it a weight. Let's call it 3. Okay. So right now I have 17. And we're just going to ask ourselves, right, is 17 bigger or smaller than this plus this? Right, and the answer is going to be 17 is bigger. Right. 3 plus 5 is 8. 8 is smaller than 17. So what we're going to do is erase this here 17 and update with an 8. And again, what we're doing is effectively saying this, right? is this path faster, or is, oh sorry, that's not the actual path. We're asking if this path is faster to G, or if this path is faster. Right, which in this case, the second one I drew right here in orange is faster. Right, so we're gonna mark this edge, and look here, right, all the edges attached to C are marked in blue, so we're going to circle it in, cross it out, and call it visited. Okay, and then the last guy we gotta tackle is D. So for D, right, we only have one edge we gotta talk about, which is this guy. And then we're gonna ask ourselves the question, right? This edge connects D and A. A already has a number, so we're gonna ask, from A, if we took a detour to D, is that faster than what we have now? Okay, I'm gonna draw it again. Which this is the path including D, which is 2 8 2 3. 8 2, yep, this and this. Or is the path we have for A right now, we go from A to C, is that faster? That's 2 3 3. All right, and then I could give you minutes to think about this, but it should be clear, especially from the fact this has a very large age right here, that what A already has is faster. Right. Another way that we're checking, right, with numbers, right, numerically, is asking ourselves is the number that A has, is that less than or equal to this plus this? Right. Whenever we're talking about an edge that we're focusing on, which in this whole example has been green, and then the vertex he connects to through the dotted line, we're always comparing these numbers here, right? The value of the dotted edge plus the value of the vertex. And so from here, right, you can even see, we're asking effectively, is 8 less than 8 plus 7? 8 plus 7 is 15. That's bigger. So we're not going to update this guy. Right. Why are we not updating? Again, it's because if we start at A and go to D first, we're going to get a slower path. So we're going to, kind of disregard this edge. All right, and then D is going to be marked because we touched all the edges. We're going to cross it out, call it visited. Look here, right? We've looked at every single edge, so we are done. And what do we find? We found that this path that I'm about to outline right here is the fastest way to go from A to G. Right, so A, C, E, G is the fastest. And then we'd be done.